Moving on to how each of those pieces of data relate to the cardiovascular system, respiratory system, and the energy systems. So the cardiovascular system then. At the start of the test, my hypothesis was a null hypothesis based off of normative data for heart rate. Therefore, I predicted that heart rate would initially increase before plateauing after approximately 3 minutes, falling rapidly after the exercise finished. The method of measuring this: we measured the participants' heart rate every minute of exercise, also measuring 1 and 2 minutes prior to and post-exercise. We did this using an oximeter, as this equipment allowed us to measure oxygen saturation as well as heart rate simultaneously. The heart rate data from the 3 participants differed greatly. There was an anticipatory rise due to the emotional release of noradrenaline, which is controlled by the hypothalamus. The sensory neurons detect the activity and send the impulse to the central nervous system, stimulating the release of adrenaline and increasing the stimulation of the SA node. This in turn will increase the heart rate in preparation of exercise. This normative data that you would expect to occur did happen for each of the participants. You can see that on Summer's heart rate, pre to 2 minutes, it had an increase, and that is the same for Max. Josh's doesn't show this increase. However, pre to 2 minutes involves the start of exercise, not the anticipatory rise. When we looked at the anticipatory rise before, each of their heart rates was above their resting heart rate, suggesting that they did follow normative data and have that anticipatory rise. Summer and Max's heart rates both increased as exercise started. This initial increase lasted longer than normative data would suggest, as their heart rates only began to show signs of levelling out at about 6 minutes, in opposition to the 3 minutes suggested by our hypothesis, and therefore normative data. Physiologically, this is a result of the demand for oxygen at the participants' now working muscles not being met. Perhaps the reason for this initial increase lasting longer than expected is because we worked the participants too hard initially, trying to reach their target zone, meaning there was still an increasing demand for oxygen due to the insufficient supplies for the intensity of exercise. Between the 6-minute and 20-minute mark, Summer showed a small decrease from 174 to 173 beats per minute, only showing fluctuations of about 10 beats per minute throughout, implying that her heart rate does plateau. Summer again shows correlation with our null hypothesis, as her heart rate decreases by 20 beats per minute after 2 minutes of rest at the end of exercise. Between 6 to 20 minutes, Max also shows a slight plateau, as his heart rate only differs by 12 beats per minute, again suggesting a plateau, but not as clear of a plateau as Summer's heart rate. This plateau is due to the increase in heart rate supplying enough oxygen to the working muscles. This obviously in turn increases stroke volume. However, as stroke volume and heart rate both continue to rise, stroke volume eventually has to lower because the heart cannot fully fill while it's beating that fast. It can't fill with enough blood due to the increase in regularity of contraction. Therefore, there is a continued increase in heart rate to compensate for that restriction of the heart chambers. Furthermore, as the supply of oxygen to the working muscles is finally met at that plateau, there's a very minimal increase in heart rate, which is why there is slight fluctuation. This supports our hypothesis that there would be a plateau during steady-state exercise. Cardiac output is a combination of both heart rate and stroke volume. Therefore, it increases or decreases in correlation to those two. So due to heart rate and stroke volume being able to provide the relevant supplies of oxygen and relevant blood to the muscles during this plateau stage, cardiac output also remains the same and plateaus at this point. Furthermore, like previously mentioned, the body will undergo vasoconstriction and precapillary sphincters will be stimulated at organs that are less essential and not needed in this situation. So, for example, there will be vasoconstriction at digestive systems where vasodilation occurs at the working muscles to allow more blood flow and more oxygen there. Venous return will also plateau at this point because there is a sufficient amount of oxygen at the muscles during this plateaued stage. So everything else plateaus because there is a consistent amount of blood being pumped around, so there's a consistent amount returning to the heart. While two of the participants, Summer and Max, had similar to normative data, Josh did not. He had very different results. During steady state, he actually had a continued increase in heart rate. This may have been due to experimental method. Josh could have been working too hard, as when he was exercising he had already warmed up where others had not. This was a miscommunication between the methods of our group testing, meaning his initial heart rate was already affected because of this warm-up. During the test, we clearly did not get him to work in the required training zone of 65% of his heart rate, maximum heart rate. Therefore, he could potentially have been working anaerobically, which would explain the continued increase in heart rate. Furthermore, we can assume that physiologically, Josh is not meeting the demands of the exercise. His heart rate is increasing to compensate for the shortage of oxygen at the working muscles. Oxygen is being used up in respiration for contractions of muscles more than oxygen is being supplied. Therefore, his heart rate continues to increase further to try and supply that oxygen. He can't increase stroke volume as the heart can't fully fill due to the already heightened heart rate. Therefore, heart rate has to increase further, also increasing cardiac output. Respiratory system. Again, we used a null hypothesis based on normative data to predict that breathing rate would initially increase and then plateau after 3 minutes, falling quickly to resting after exercise ends. To measure breathing rate, we observed the rise and fall of their shoulders or chest for 1 minute. We measured this every 2 minutes, also measuring 1 and 2 minutes prior to and post-exercise. Prior to exercise, the respiratory system will respond with a very slight increase in breathing rate. This increase is caused by a thought or feeling about the exercise that causes a stimulation of nerves, hence why we call the emotional response getting nervous. This emotional stimulus sends a message to the respiratory control center inside the medulla oblongata, which is then sent to the dorsal respiratory group. The DRG controls inspiration and sends an impulse down the intercostal nerve in response to the message from the RCC. This causes the external intercostal muscles and diaphragm to contract, allowing more oxygen to fill the lungs due to the now differing pressure. You can see that Summer follows normative data here, as she experienced this anticipatory rise. However, due to lack of recordings for other clients, the same cannot be suggested for them. As exercise begins, Summer's breathing rate rises, as do Josh's and Max's. Summer's increases from 16 to 24, Max's increases from 40 to 44, and Josh's increases from 26 to 34. This is due to the increased demand for oxygen as exercise begins, which causes breathing rate to increase to supply more oxygen due to increased frequency. This is because the muscles will start to require more oxygen due to the intensity of the exercise increasing. This therefore results in the detection of the increase in oxygen by the chemoreceptors due to it being used up in exercise, along with the increased levels of carbon dioxide and lactic acid that will start being produced by muscles as a byproduct of respiration. The proprioceptors will detect the increase in movement, and the baroreceptors will detect an increase in blood pressure in the blood vessels and the stretch of the lungs. All the receptors then send an impulse to the RCC down to the DRG, which controls inspiration. Again, this impulse is sent along the intercostal nerve to the external intercostal muscles in the diaphragm, making them contract, causing the ribs to move up and outwards, increasing the pressure outside the lungs and decreasing the pressure inside the lungs, causing the air to forcefully be inhaled as air moves from a high partial pressure to low partial pressure. This increase of air that's being inhaled will increase the breathing rate. And this is obviously what occurs to Summer, Josh and Max as they start their exercise. At minute 10, Summer, Max and Josh's breathing rate all begin to plateau. For example, Summer's plateaued to 33 breaths per minute from the 29 2 minutes before. At minute 20 they all decreased slightly but would still suggest a plateau, as the maximum difference in breathing rate was in Max's, which was a difference of 4. This correlates slightly with normative data, as normative data would suggest a plateau when steady state is reached. The breathing rate will start to plateau because of the consistent amount of oxygen being delivered. The demands of the exercise are being met by the supply of oxygen. As a result, the chemoreceptors detect the sufficient levels of oxygen and send a message to the respiratory control center, where the ventral respiratory group will detect that the breathing rate does not need to increase. Therefore, this is why breathing plateaus if the exercise is aerobic, such as in a marathon. We wanted this exercise to be aerobic, which is why this occurs in this test. Energy systems. We used null hypothesis to predict that participants would mainly use the aerobic energy system. To measure their energy systems, we measured their blood lactate using a blood lactate analyzer, which was measured on minutes 2, 10, 16 and 20. Both Summer and Max's have an initial increase in lactate levels as exercise begins, after 2 minutes. Summer's increases by 12.5 and Max's by 16.2. This is likely a result of the use of anaerobic glycolysis initially due to insufficient amounts of oxygen at the muscles. Furthermore, lactic acid is a byproduct of anaerobic glycolysis, which is why those lactate levels initially increase. Josh's differs from the other participants as his lactate levels only increased by 0.5%. Josh's lactate relates more closely to normative data, as you wouldn't expect a high lactate level in aerobic exercise as late on as the others have. You might expect an increase at the start of exercise, but this should quickly fall again after the 3rd minute, which Summer's and Max's do not. Again, this would imply that Summer and Max are working anaerobically, as their lactate levels remain high. This is a result of them working too hard, correlating with their high RPE scores that we saw previously. Their bodies have insufficient supplies of oxygen for the intensity of exercise they are participating in, so they are having to use anaerobic glycolysis, meaning their lactate levels are high, as lactate is a byproduct and waste product of anaerobic glycolysis. You might expect their use of anaerobic glycolysis at the start of exercise during the first 3 minutes. However, after that initial 3 minutes, like we mentioned, there should be a plateau where aerobic glycolysis comes into play, because there is the presence of oxygen and a sufficient supply of oxygen. Finally, evaluating our hypothesis, none of them I feel were correct, as I feel that the data doesn't correlate close enough to normative data. I believe the cardiovascular and respiratory hypothesis were both wrong, because the heart rates and breathing rates didn't show any signs of plateauing until minute 6, where normative data implies that it should be around minute 3, and it didn't show a consistent plateau in all participants as some faltered. In relation to the energy system, I feel our hypothesis was wrong there because the lactate levels were too high in 2 of the participants, implying they used anaerobic glycolysis instead of aerobic glycolysis.